Okay, so we start this new lesson, and that is you usually get a question like this in the national exam. They are talking about the asymptotes of functions. Okay, to motivate you, let me just start with the example why we need the notion of asymptotes in the first place. So we want to understand the behavior of the graph of a function even better, okay, because we learned we can find the local extreme points and the terrace points, inflection points, and then using them we can have a qualitatively good picture of the graph of the function. But still, I just want to give you an example. This is sometimes not enough. If we have an extra guidance to draw the graph better, it would be valuable. So for example, let me give you an example. I don't know, might be this example is good. So we want to draw the graph of the function, sketch, of course, not precisely draw. We want to sketch the graph of this function 1 minus e to the power of minus x using the tools that we have developed so far. So what we want to do, we just take the derivative and try to find the extreme points and then draw the sine table. Using that, we can draw the graph. But you will see that even I do this in this one, it's not giving me something completely wrong, but it is not that precise. I can check it with GeoGebra and then you can feel that, okay? So what I do as normal, I start with differentiation. So the derivative of this one is 0, minus 1 comes down, and the function repeats itself. So that's the derivative. And then the next step is to put the derivative equal to 0 and then try to find the important points. But then what happens? There are no points. Because e to power minus x can never be 0, yes? Because the base is not so. No solutions. Okay, so it means that there are no local extreme points, there are no terrace points, and that is correct. This really doesn't have any one of them. But the point is that, okay, then what can I do? Okay, so let me just draw the sine table. So x, f prime, and f. And then there are no interesting point to put here. So then what to do? I need to determine the sign of the derivative everywhere. But what is the derivative? The derivative is an exponential function. So regardless of the values that I choose for x, this derivative is always positive. So this means that I have a big positive sign here, meaning that it is always positive. And when the derivative is positive, it means that the function is constantly increasing. None of them is wrong. But if I want to plot the graph of this function using this information, it's not probably that useful. Okay, I get some ideas. So first of all, for example, because there is no point here, so let me just try to put 0 at least to get some kind of information, and this becomes 0. Because e to power 0 is just 1. So definitely my graph passes through the origin. Because when I put 0, I got 0. And I know that the function is constantly increasing. That's it. But I hope that you see that I have a lot degrees of freedom to draw that, yes? So, and then which one is good, I don't know. So for example, the function grows up and then continues like that. So this is increasing. I don't know, the function might start from here and then do something like that. That's also increasing all the time, and I'm passing through the origin, okay? It's not totally wrong, but if I can have some kind of leverage in my hand to make it better, why not, yes? And that's the idea of asymptotes. So by the way, if you don't mind, let me just put this in the GeoGebra, and then you can see that even though I'm not totally wrong, but it is not the one that I want, especially when we draw the precise way here. So if I go to GeoGebra, and hopefully this is not, okay, it's working. So the function y equals to, I have 1 minus exponential to the power of minus x. So that is the real graph that you can see here. You see that it is not totally wrong, but there is some kind of behavior that in this lesson we want to focus on. So mainly this behavior. By the way, you might get this wrong impression that's a flat line. Okay, that's not a flat line. Why is that? Because if that's going in flat line, you should see it in the equation. You know that the flat line means y equals to a constant. So definitely it's not a flat line, but then I think we can, you see, I don't know, zoom in or zoom out, which one is better?
Zoom in.
Zoom in. So you see that if, as far as I zoom in, this distance is appearing actually. So you see, this distance is not zero. So if you see, if I zoom in and go further and further, you see this is not flat. But I saw it flat. But of course, at least you know something. Yeah, there is something really wrong with my graph, yes? Yeah, because if this is the behavior, what is the difference between these two behaviors? You see here, I get this, if I draw this one, you get this wrong impression that my graph continues increasing and goes beyond any number that you imagine. But by this way of drawing my graph, I am giving you this impression, yes? So because when I draw the graph like this, you would say that, okay, Bobak has drawn it like this, so we continue this graph from here. When the graph goes like this, it means that eventually it will pass every upper bound. It doesn't matter how big that number is, it will go. But apparently it seems that in GeoGebra, it shows that this is not happening, yes? Yes, it doesn't pass, even it doesn't go beyond 1. Is that clear? But this graph that I have drawn it here, even though not totally wrong, but it gives you the wrong impression that it is going beyond 1. And by the way, how do you know that this shouldn't go beyond 1? By looking at the function itself here. Yes?
When x is growing, minus e to the power of x is just very small.
Yeah, or simpler. This is always a positive number. Yes, e to the power of minus x, independent of the choice of x, is positive. And then I have 1 minus a positive number. So definitely it should be below 0. Yeah, below 1. Okay, but so this is why I'm saying that sometimes we need to do things better, more precise. Even if I draw it with this new notion of asymptotes, it will not be precise, but it will be better than that one. Okay. Okay, so this we want to learn, and let me just show you on this picture. So if I draw the graph of y equals to 1, this black line, of course, again, as before, you know that they are not touching each other, but the distance between the green curve and the black line is getting smaller and smaller when I go to the right. We say that this black line is an asymptote for the curve. And this kind of behavior is called asymptotic behavior. Yes? So asymptote is a line that's the distance between that line and the curve gets smaller and smaller when we go farther and farther. So that's the idea. The distance between the function and its asymptote approaches 0 when I really go far away. That's the meaning of asymptote. Okay? And then I have 3 kinds of asymptotes. One that you just saw in GeoGebra is a horizontal asymptote. The answer is actually, the reason is clear because it's horizontal. And then, what do you think I will have? I have horizontal asymptote. If this happens, I might have a vertical asymptote, and in other case is an oblique asymptote. Now, these are the 3 cases we want to consider. Horizontal asymptote, vertical asymptote, oblique asymptote, either that one or that. These 2 we will leave for the next lesson. These are a little bit harder, but these 2 we hopefully cover today. Okay, so is that clear what we are going to do? Okay. And I think because this graph motivates the horizontal asymptote, we want to have a definition of a horizontal asymptote. Okay, so first of all, horizontal asymptote is one of these 4 pictures you have to have in mind. What do you expect to see when I say a horizontal line is a horizontal asymptote? So assume that this is your line. It might happen that your curve, I don't know what is happening somewhere, but it might happen that the curve goes like that. This means this black line is a horizontal asymptote for that branch of the curve at least that you see in red, yes? This is one way of being horizontal asymptote. Another way might be this case. So I have this, so for example, this, let me call this point B, and then I will have also this one B. But it might happen that you see this kind of behavior, but from below, exactly as our example. You might have this scenario, yes? Might be the graph is approaching to this B, but from below. Okay? And then there are, of course, two other possibilities you can guess. What are they? I can still have my horizontal line. Yes? And then it might happen that when I go to the left, I see this behavior, not when I go to the right. And then finally, you can guess the last one, hopefully. Might be this, I get this idea. So it might be this happens. When I go to the left, the branch of my curve is getting closer and closer. So what matters is this distance. You see, this distance is getting smaller and smaller. Here the distance is again smaller and smaller. When I go far to the right, but sometimes it might happen that when I go far to the left, this is happening. Yes? And in all these cases, be careful. If they ask you write an equation for the horizontal asymptote, you should write y equals to b. Because that's a line, you need to give me an equation for the line, so you cannot just say b. You have to write an equation for the line, so that y equals to b. Okay, now can you tell me if I want to find that line systematically, how should I do that? For example, before doing these calculations, I give you the function, you don't have access to the graph of the function. I ask you, can you find a horizontal asymptote for this function? How you systematically answer this question? Because horizontal asymptote means what is happening on far ends, far to the right or far to the left or both. By the way, it might happen that you can have both of them. For example, you can have this line and one branch of your graph goes like this, another branch of your graph goes like that. So this line is actually horizontal asymptote, both on the far end on the right and far end on the left. So all possibilities can happen. You can have a horizontal asymptote for the right branch, for example, and you can have another horizontal asymptote for another branch. I mean, all these kinds of behaviors, these are asymptotic behaviors. Okay, but systematically, how can I answer that? Yes?
Maybe if you try searching for a limit.
Limit, yeah, exactly. Limit far to the end means x goes to plus infinity. Limit far to the left means x goes to minus infinity. And if it happens that the limit, as we learned in the previous year, if the limit turns out to be a number, then I am done. That number, y equals to that number, is a horizontal asymptote. Yes? For example, if I want to calculate or determine actually the whole horizontal asymptotes of this function, I have to calculate two limits. Yes? I need to ask myself, what is the limit of my function when x goes to plus infinity? And once more, I have to do the calculation when x goes to negative infinity. And it might be different. These numbers might be the same, might be different. You have to check both of them. Because it might happen that you have only asymptote on the right but not on the left, or on the left but not on the right. It's not clear. We have to calculate both of them. And then the limit of something goes to infinity, if you remember we studied before, you need to think in this way. I have a constant divided by infinity, it goes to 0. So this is the idea of calculating limits when it goes to infinity. You need to convince yourself that you are facing a fraction whose numerator is somehow constant or not growing that much, but the denominator is growing too much, so they go to 0. And by the way, when I say infinity here, it is also minus infinity, yes? If a constant divided by a negatively large number, still it is negligible, but might be negative negligible, yes? But still it's negligible. Okay, so now, I don't know, because there is no way for me to teach you how to calculate limits, except for that we learned in Math 3C, but this is... Okay, now I ask you, I want to calculate the limit of this function when x is extremely positively large. So how should I calculate that? You need to say, okay, e to power minus x has another name, which is e to the power of positive x. And then when x approaches positive infinity, what happens? E to power infinity becomes really, really big. 1 over a very big number is negligible. In the limit, we say the limit is 0. So what is left? 1. Yes, this is the limit. But you shouldn't stop here. You should say that, okay, y equals to 1 is a horizontal asymptote. Asymptote, let me just write as ASY. And I have used intentionally this article A, but you already know from the graph. Is there any other horizontal asymptote in this picture? No. Okay, but still we don't know it is the only one unless I calculate the next one and it doesn't give me any answers. Okay, so you have to check it out. For the time being, I have to write a horizontal asymptote. Okay, we go back here. So I calculate this one, but this, what happens if I want to calculate this limit when x goes to negative infinity? So what's the answer? If x is negatively large, minus x is positively large. And e to power that positively large becomes even larger. So can you tell me what the limit is? What is the limit? What type of infinity?
Positive? No, sorry.
Negative, yes, because x goes to negative infinity. Negative times negative infinity is positive infinity. E to the power of positive infinity, it becomes extremely big, which is positive infinity. And if I say 1 minus infinity, what is the answer to 1 minus infinity? Minus infinity, so that's the answer, is minus infinity. So now I can go back and fix this one because this is the only one, so it is better to write the horizontal asymptote. Yes? So y equals to 1 is the only horizontal asymptote for this function, and it is actually clear on the graph. And then let us also see that behavior. By the way, it goes faster to minus infinity than we expected, yes, because that's an exponential. So you see that when x goes to minus 4, I don't know how much is down there. It's not that much, minus 17, around minus 20 or something. But if I go to the left far end, so you can imagine that this will go too far down, yes? So it becomes negative infinity. So these kinds of behaviors, what happens to the function at the far right end, left far end? So this is actually something that you need to know. Okay? Okay, so let me just try to give you some examples. So if I want the definition of that, if I ask you find horizontal asymptote, the recipe is clear. You have to calculate two limits. One, the limit of the function when x goes to plus infinity, and one, the limit of the function when x goes to negative infinity. The ones that end up with a finite number are your answers, but then you have to write y equals to that number is your horizontal asymptote. Okay? So let me just give you one more example here, please. A very simple one first. So I give you f of x, and I write you x divided by x to the power of 2 plus 4. And then I come back and use GeoGebra to draw that. So we want, if you don't mind, because that's boring, let me just make it 2x plus 1. Okay, so if we want to find a horizontal asymptote, or all of them, of course, for this function. So what I'm supposed to do, the recipe is clear. I have to take limits, but I have to consider both of them. In the examples in your book, both of them are usually the same, especially if you have polynomial type of functions. Okay? But this is not a necessity, okay? So just let us try to do that. I don't know how many of you remember how to calculate limits at infinity last time we talked about, and not in Math 3C together, because we were following this exponent book, so it was extensively discussed there. Okay, so, yes?
Weren't you supposed to divide by the lowest common power of x, right?
No, the highest
Oh,
power.
the highest common power.
Because the idea, as I told you, a constant number divided by infinity is 0. This is just something I want you to remember. Infinity is not a number, but you need to imagine. Okay. This is one way, but let me also teach you something else here, so we can actually see. If x is extremely large, 2x is extremely large, but 1 is constant, which one of them will dominate? Yes, 2x or 1? 2x, yes, because x goes to infinity, 1 is constant, so 1 is negligible when compared to 2x. So I can say that, okay, for all intents and purposes, this is actually 2x. And then what can I say for the denominator? X squared plus 4. It's more or less x squared, because this 4 is nothing. And then x goes to infinity, plus infinity. But you know that this x and that x can be simplified, so it becomes 2 over x, x goes to plus infinity, but what the answer is? The answer is 0. But you shouldn't write up to there, you have to write y equals to 0 is a horizontal asymptote. But what is, by the way, this one, y equals to 0? Y equals to 0 is the x-axis. So it means that the x-axis itself is a horizontal asymptote for this function. But the same analysis also works here. Yes? Again, even though x is infinity negatively large, so compared with 2x and 1, 2x will dominate in a negative way. Yes? So still it becomes 2x. And then this is positive infinity, because even though it's negative, I'm squaring it. So again, x squared will dominate. And then you get 2 over x again. This time, the only difference is that x goes to negative infinity. And the answer becomes again 0. So there is only one term, so I can come back and fix it and change the article to there, yes? So I know that this is a function, this is different, this behavior is different from that behavior. Because in the previous example, the behavior on the far right and the behavior on the far left were quite different. Yes? But here apparently, the behavior on the right end and the left end are the same. But what is the difference between I put it in GeoGebra? Can you see a difference? Because you know that for having a horizontal asymptote, we can have one of these 4 possibilities. Okay? Okay, now can you tell me what do you expect before I put it in GeoGebra? On the right branch, on the far right, which one of these things is happening, do you think? Because here, we go to the right, but we are approaching from below. This one, we go to the right, but we are approaching from above. So this behavior is different from this behavior. We can detect the difference, even though in both cases, the same line is a horizontal asymptote. So now by this calculation you see on the board, only on the right end. Okay? On the right end, do you think this is happening or that is happening? Okay, so you see that the limit is 0. But do you think I am slightly above 0 if I'm slightly above 0, this is happening. If I'm slightly below 0, this is happening. Yes?
Above.
How do you know that?
Because if you put 2 over 1, for example,
Yeah.
it's above the x-axis.
Yeah, okay. So you say that if because 2 is positive,
Yeah.
x is infinitely large but positive.
Yeah.
So positive divided by positive is positive. So even though I write 0, 0 is neither positive nor negative, but this is the far, far end. This is the not possible to reach. So before that, I am always slightly above 0. Yes? So, but what about this branch? So when I go to the far end, the far left, the answer is again 0. But still there are 2 ways that I can approach to my asymptote. Either from above an approach to my asymptote or from below an approach to my asymptote. Which one of these cases do you think is happening for this case? Again, the same thing. Look at the last step. 2 over x is still 0. But what type of 0 is that? It's not a correct question because 0 is neither positive nor negative, but this 0 is essentially infinitesimal. But infinitesimal can be slightly positive or slightly negative. It's just slightly negative,
yeah.
Yes? Because it shows that this is positive again, but the denominator is a huge negative number. So if this is going to be an infinitesimal, it's a negative infinitesimal. So our prediction is that on the right end, this is happening. On the left end, this is happening, yes? Am I right? Okay, so let us check. We go and put this in GeoGebra here. Let me get rid of them. So y is equal to, what is that? 2x plus 1 and then divided by x squared plus 4. Okay, so that is actually interesting graph. Oh, sorry, I made a mistake here. It was so bizarre. So plus 4. Am I right now? Okay, so that's the graph. Okay, so let me just make it a little bit more clear. Okay, and this is the graph that you see, and if I can squeeze it a little bit so that you can see the behavior even better. Okay, so you see that I have exactly what I predicted, yes? What I expect you to do is by looking at the graph, you realize the x-axis is a horizontal asymptote. Can you feel that? Yes, because the distance between the line and the curve is getting smaller and smaller, both on the right and on the left. And the prediction was right. You see, on the right, left, on the right, what do you say? On the far right, it is approaching to x-axis from above, and on the far left, it's approaching to the x-axis from below. Okay? So our predictions are correct. Is that clear? Okay. So, for example, a little bit more tricky example. What do you think will be like this one? F of x equals to sine of x over x squared plus 1. We want to see if there is a horizontal asymptote for this function. Okay, then the recipe is clear. What I'm supposed to do, I have to take the limit. Okay, so if you don't mind, let me, for simplicity of writing, from the beginning, I write plus or minus. To see if it is working, I will continue with plus minus until the end. But if it is not working from the middle, I will separate them. But at least it saves me some time, okay? Okay, so I will write it here to see what happens. Okay, can you tell me what is this limit? By the way, the best way to calculate limits at infinity is to rely on your senses, yeah? So what's happening? Do you think, is it approaching to a good number or not? What's the number?
Infinitesimal.
Why?
Because
When you say infinitesimal means the limit is
0.
0. But why?
Because sine of x will approach 1.
Not approach 1. It's maximally
It's
1. It cannot go
maximally 1.
beyond 1 or below minus 1.
Yeah.
So it is trapped somewhere between minus 1 and 1. And then you are dividing it by an extremely large number. So whatever that number is really doesn't matter. Even if it is on the far extreme case, it is just 1. So this means that the limit is 0. Okay? But predicting the behavior is, I think, is a little bit hard. Some people say that this is not an asymptote. Why is that? Because I don't know. Do you get this feeling? If I draw this, and I draw this picture for you. So I think my prediction is this is happening all the time.
Yeah.
So do you get this is an asymptote? Because you know that in asymptote, it seems that it should be tangent, yes, at some point.
Yeah.
So my feeling is that when I draw this, because this sign is going up and down, it's oscillating, it will go up and down 0 all the time, yes? So I cannot say that it is always above or always below, yes?
Yeah.
And then I don't know, from humans' point of view, I don't think we call this asymptotic behavior. I don't know, it depends. Some books they say that no, asymptote means after a while, after some point, there are no intersections. Yes? So might be if I have this line like going like this and getting smaller and smaller and eventually goes like that, yes, I call it asymptote. But if up and down is actually continuing all the time, there is no asymptotic behavior. Yes?
So I don't understand. Is there not a concrete definition of an asymptote?
Yes, that is a concrete, but this is not in your books. The concrete definition is as I told you. The limit should be that number, and there should be a number after that there is no intersection.
Okay,
That is the exact definition of an
so
asymptote.
if there's an exact definition, why are people arguing? Is this an asymptote?
No, they are not. They are not arguing. I mean, so might be that was my mistake. They are not arguing. But I mean, this level of example is not at the level of your book, because when you calculate this one, you get 0, and if I don't talk about this, you get this wrong impression that this is an asymptote. But let me just draw it by GeoGebra. You will see this oscillating pattern happening around the x-axis. And then I hope that you understand that if I say this is asymptote, you agree with me, because it oscillates up and down, but after a while it approaches smoothly to the line. But if this up and down is supposed to continue forever, this is not asymptotic behavior. So I will not, that was my mistake. I shouldn't brought this example up. Okay. I didn't predict that before. Okay, so let me just put this in GeoGebra. Let us see what happens. So I have my function y is equal to sine of x, and then you see this is the sine function, because by the way, this is in degree. This is why you see this wild behavior. But let me just divide it by x to the power of 2 plus 1. Yeah, so something like heartbeat, yes, something like that. But let me just see that. You see this oscillation is not finishing. So it doesn't matter how much I go to the right, these oscillations are actually continuing, They go up and down, yes? So this is not an asymptotic way of approaching 0, yes? It is getting close to 0, but by oscillations, going up and down, cutting this line a lot of time. So forget about this example. That was my mistake to bring this up. But at least I want you to know that 0 is not the asymptote for this function for this reason, not because the limit is not equal to 0. Okay. Okay, so what we can do now, we can switch now to the next lesson, that is the vertical asymptote. Okay? But now you have some enough experience about asymptotic behavior. Can you give me a function that has a vertical asymptote? As simple as possible. Make it as simple as possible. Yes? Yes, Rocco?
Would it be some exponential?
No, just give me a function.
X squared, maybe?
No, okay, x squared has a vertical asymptote. This is a wrong impression. This is why I saw a question in the book. A parabola, do you think it has a vertical asymptote or not?
No.
So this gives the wrong impression, yes, because the way we draw it carelessly. But y equals to x squared, okay. If you say that there is a vertical asymptote, what do you mean? It means there is a line vertical, so that this line becomes closer and closer to this one, but never past this line. Yes, this is the meaning of asymptotic behavior. But do you think this happens? Do you think this will pass this line eventually? Yes. This will pass every vertical line that you can imagine. So there is no asymptotic behavior for this function. This length becomes wider and wider and wider when I go to the far right. Yes? So that's not possible. Okay, so you lost your chance. Let us go back to it. Yes?
Can we say that tangent over x has an asymptote?
Yes, and you just went to far extreme. It has infinitely many vertical asymptotes. That's correct. Yes? But before that, yes, that's correct. That's a good example containing infinitely many vertical asymptotes. Yes? But something in between? Just having one vertical asymptote or something? The reason that I'm asking, because I want you to come up with the idea yourself. Yes?
Maybe 1 over x.
1 over x is the simplest possible example I can also think. Yes? Y equals to 1 over x. Y, but by the way, what is the vertical asymptote for this function? Would you guess yourself?
Y equals to 0. No, sorry, x equals to 0.
X equals to 0, yes? And how did you come up with this idea? Because what do you expect of a vertical asymptote? Let us try to understand it before I write the formula. So, let us imagine that I say that this line A, x equals to A, when I say that this is your vertical asymptote, what do I mean? I mean one of these 4 possibilities is going to happen. Either this kind of behavior you see, or this kind of behavior you should see, or this kind of behavior you see, or that kind of behavior. Otherwise, you shouldn't call it asymptote, yes? So when I say this line is a vertical asymptote, it means one of these 4 possibilities is happening exactly like we had for horizontal asymptote, yes? Okay, but let us try to formulate it. Can you tell me if this is the case, what is happening to your function? When I am getting closer to this A, what is happening to this red branch of my curve? So when I am here, this is my height. This asymptotic behavior means when I go, this distance becomes smaller and smaller, yes?
Yeah.
But it goes forever. So this means that when I am approaching A from the right-hand side, what is happening to length of these black curves?
The height
Increases.
approaches infinity.
Yes, it goes to infinity. So it means that if this is happening, this means this is happening. The limit of f of x when x goes to A from the right is positive infinity. Yes? Or might be this is happening. Still I call this a vertical asymptote. If this happens, what is the mathematical condition for this behavior? What is that? This behavior from here to here. It's still the limit.
The height approaches 0.
No, the height is not approaching 0 again. So I am getting closer to A, but the height is still increasing. Yes? But the way that I am approaching A is different. I am approaching A from the left. So the limit of f of x when x goes to A from the left is positive infinity. I mean, when you say this black line is a vertical asymptote, the person who is hearing this from you expect one of these 4 cases. Because otherwise, why you should call it asymptote? Okay, in this case, it means mathematically this is happening. In this case, it means mathematically this is happening, and I want you to tell me for the other 2. So assume that this is happening. How should I understand, how should I detect it mathematically that this behavior is happening? The limit. You understand me or not?
No.
Yes? Why not?
From which direction are we looking at?
No, there is one. The direction is clear. It means no, because I want to talk about the asymptotic behavior. When I say the asymptotic behavior, you want to say what is happening to my function that results in this kind of behavior. It means that when I approach A from this right side, what is happening to the value of the function? It's going down, yes? So this means that f of x, don't expect me to explain more. This is Friday evening, okay? So I'm very tired now, okay? Just try to understand. Yes? The limit of f of x, x goes to a from the right goes to minus infinity. Yes? Is that hard to understand? Okay, the last chance. How should I detect this behavior?
Negative infinity.
Huh? Yes. X goes, with just all the details. F of x, x goes to what?
A negative.
A from the left
Yeah.
is
Negative infinity.
negative. So that is also the definition of a vertical asymptote. So if I want to make it more precise, I would say that the line x equals to a is a vertical asymptote of f of x if at least one of the following conditions holds. Yes, so that's the definition, but I didn't want to just write the definition on the board and say that follow it. I just want you to understand the notion of the asymptote. The asymptotic behavior means the distance between my function and that line is shrinking when I go farther and farther. But in this case, it translates itself into one of these four equations. If one of these happens, even if the other ones happen or not, we don't care. If at least one of these happens, we say that x equals to this number, whatever it is your vertical asymptote. Yes? And then can you tell me how did you come up with your example? Because that's also important. You ask yourself what to be able to get to that answer.
I was thinking that since we don't want the asymptote to actually, or we don't want the function to maybe pass through the asymptote. I
Yes?
could think of a function that isn't defined at that point, and
Yes, but not only not defined, because for example, if you have a square root of x, a square root of x is not defined as minus 2. But you wanted something else, not only not defined, but when I approach that one, it becomes huge. So this is why you thought about the fraction and said to yourself, okay, is it possible for the denominator of the fraction to become 0? You would say yes. So it means that when I am getting close to 0, 1 over a very small number suddenly becomes huge. Then I will get that behavior that I need. So that's actually the motive behind that. And I think most of the examples in your book are fractions. Okay, we can have exceptions because it's always easy to send a fraction to infinity. By how? By making the denominator smaller and smaller. So one of the possible type of functions that have vertical asymptotes are fractions. Yes, that's why. For example, if I give you a function, a polynomial function, like p of x equals to x squared plus 3x. Is there any number that you can put for x and then p of x becomes infinity? There is no numbers. There is only one thing that you can say, make x infinity. Yes? And infinity is not a number. You cannot say that x equals to infinity is my vertical asymptote. Yes, if you like it, yes. X equals to infinity is your vertical asymptote. But this is not good. So, for you, if I ask you what is the vertical asymptote for this function, it means think about a number so that when x is close to that number, the value of the function becomes infinitely large. But is it possible? No. It doesn't matter. Even if you choose x to be 1 million and then you put it here, it becomes a very big number, but it is not even close to infinity. Or even if you make it 1 trillion, it becomes even much bigger, but it is not still close to infinity. So there is no number so that when I get close to that number, the value of this becomes infinite. Yes? So this is why there is no chance to have a vertical asymptote for this function. But as Robert mentioned, there is a very simple way to make 1 over x extremely big by going close to 0. When I go close to 0, the limit of 1 over x, x goes to 0, is of infinity type. But of course, if I go from the positive side, it becomes positive infinity, and if I go to the negative sign, it becomes negative infinity. But one of them is enough. I don't need to have 4 of them. Here I have 2 of them, but only one of them is enough to say that x equals to 0 is a vertical asymptote. Okay, so the question is this. When I give you a function, it is a little bit harder than the previous one because the recipe for the previous one was crystal clear. You just take the limit, x goes to infinity, x goes to minus infinity to see what the number is. But here you have to do some guesswork. If I give you a function and I ask you to find the vertical asymptotes, you need to ask yourself, what is that number for which when x goes to that number, the value of the function becomes infinitely large or infinitely negatively large, yes? But this is why it's a little bit harder than a horizontal asymptote. Okay, so first of all, let me just draw the graph of 1 over x using GeoGebra, get the feeling. By the way, just tell me, do you expect horizontal asymptote for the function that Robert mentioned as well? So Robert mentioned 1 over x for an example of a vertical asymptote. That was correct. We learned that x equals to 2. But is there any horizontal asymptote for this function as well? Horizontal asymptote is clear. Take the limit, send x to infinity. What's the answer?
Yeah, the x-axis.
The x-axis means y equals to 0. So this is an example that has both horizontal asymptote and a vertical asymptote, and both of them are the coordinate axes, yes? So let us check. So if I go back and clean this, so what we do, let's go back to home. It's a good place to go in afternoon, yes, Fridays. But unfortunately we have to go home on GeoGebra. So y equals to 1 over x, and that is the behavior that you see. So you see that, hopefully you can realize, do you feel that this x-axis is a horizontal asymptote? On which branch? On both branches. And this one is a vertical asymptote, again on both branches. So that's the famous graph. By the way, this is one of those famous graphs that you should have in mind. So like x squared, 1 over x is also a good function to have in mind. And then you see that this function is not continuous. Yes, because the limit x goes to 0 is infinity. Okay. Okay, now let me go back to Gustav's example of tangent. So why, by the way, this is a little bit tricky because I told you. Okay, let me just solve one problem of this type. I give you this function, x plus 3, and then x to the power of 2 minus 9. This is a good example. And I ask you to find all vertical asymptotes of this function. Okay, let me ask you for practice. Is there any horizontal asymptote for this function? Horizontal asymptote has a very clear recipe. Take the limit, send x to plus infinity, send x to minus infinity, and see if the answer is a number. But is the answer a number? And what that number is?
0.
0. Yes, because again I told you this will dominate. It becomes x. In the denominator, x squared will dominate. And then it becomes 1 over x. When x is infinity, this becomes 0. So your guess is correct. Y equals to 0 is the horizontal asymptote. Okay, but the question was not a horizontal asymptote. My question now is find the vertical asymptote, if any. So how do you approach the problem? How? You need to look for some candidates, because you need to ask yourself about, are there numbers for which the value of the function blows up in either case, positive or negative direction? If the answer is yes, those are good candidates. Yes? So you see, in horizontal, the recipe is to send x to infinity. But in the vertical one, you ask yourself, is there any number for which, when the x becomes close to that number, the value of the function becomes extremely large or extremely low? Yes. What are the candidates?
I mean, one is 0.
No, 0 is not a very big one. If I put 0,
Like
it becomes 3 over minus 9. Is it big?
Oh,
Yes?
3.
Okay, two possibilities.
Uh,
Because I told you that when you have a fraction and you want to make it extremely large, the target is to go to the denominator and then start tampering with the denominator to make it very small. If you can make the denominator very small, then you can have the hope that the whole function becomes very large. So what I do when I want to do the vertical asymptote, I will go and put the denominator equal to 0. Okay? And then I see how many answers you get. Minus 3 or positive 3. These are, if I ask you what are these, you would tell me these are candidates for possible vertical asymptotes, yes? So far, candidates for vertical asymptotes. But it is not confirmed yet, because the definition is not put the denominator is equal to 0. You need to be responsible for sending function to infinity. Okay, so this means that you have to come back and check out if they are false or real. How? By taking the limit. But the limit of my function, when x goes to what? 3. From right or left, one of them is enough, but we don't know which one, so we have to consider both. And another time, I have to calculate minus 3 plus or minus. Yes? Okay, I have two numbers. If the answer is plus infinity or minus infinity for one of these cases, then x equals to 3 is a real vertical asymptote. But if the answer is a number, that is a fake one. So let us check. Okay, if I ask you to calculate this limit, how do you calculate it? For example, for definiteness of discussion, let me only consider one case. If it didn't work, I will consider the other case as well. Okay, if I ask you to calculate this limit, what's the answer? Whenever you want to calculate a limit, you need to put the number in. When you put the number in, the numerator is good, 6. But then I face a problem, it's 0. So I have 6 divided by an infinitesimal. Because when I say 0 is not really 0, because x is not exactly 3, it's a little bit above 3. Okay, so what type of limit is that? 6 divided by infinitesimal. Infinitesimal. So the answer is definitely the infinity. Okay? And by the way, you don't care what type of infinity. If you want to investigate more, you need to care. But it doesn't matter if it is plus infinity or negative infinity, it is acceptable. Yes? So finally, I would say x equals to 3 is a vertical asymptote. Okay? But what about minus 3? It's different. Look, when I put minus 3, the denominator is again 0, of course, but this time the numerator is also 0. So it is of the type 0 over 0. Do you remember we discussed 0 over 0? We have to get rid of this indeterminacy. How? It's simple. In this case, it's extremely simple. I can calculate this limit by factoring it out, by the conjugate rule, and then x plus 3 And then what happens? X goes to minus 3. And again, for definiteness of discussion, let me take this one. If it doesn't work, I need to come back again. So do you think that this limit is infinity? By the way, I can consider both. Yes, this one is gone. Am I right?
Yes.
Yes, so I made a mistake. I wanted to do it the other way around anyway. I spoiled the example, okay. Yes, I should have written it the other way around anyway. Okay, so that's also acceptable. That's also a type of infinity. Yes? So this means that yes, I have both of them. So these are real. But don't get this wrong impression that whatever you have in the denominator is working, because if I had this the other way around, then what is your candidate? But let me check it using GeoGebra, okay? Let me use this GeoGebra to check this one again, and let me ask your opinion about this and then put it in GeoGebra, okay? So let me go back here. Delete, so we go and then put this one in the example. So y is equal to x plus 3 and then divided by x to the power of 2 minus 9. Oops. It doesn't show me 2. How is that possible? Did I miss some calculations?
What do you mean, Balut?
No, there should be somewhere else. No, definitely it is wrong. Aha. No, it is not wrong, to be honest. But I should be able to detect that by calculation, couldn't I? Now I understand what is happening, yes. Yes. Because that function can be simplified actually. X plus 3 over x squared minus 9 is just 1 over x minus 3.
We put minus 3, and down there. No, on the board, and use, it's supposed to be minus 3, which becomes minus 6 over, 1 over minus 6. No, infinity, it doesn't.
Yes, that's good, that's good. So that was a good example. I'm so tired, okay. So thank you very much. So let me just recheck my calculations. You put the denominator equal to 0, you get two candidates. Then you have to check them, they are real or not. So when I put this in the calculation, I got infinity. Why? Because when I put 3 here, it is 6 divided by a negligible number, which is infinity. Because the answer of the limit is infinity, x equals to 3 is acceptable. And now, when I want to do this calculation, I messed up here. Yes, you are right. So what I do is minus 3. So everything is right. I put minus 3 in my limit. The problem is that the numerator becomes negligible. The denominator is negligible. Do you remember we talked about negligible over negligible, which is indeterminate. We have to take this indeterminacy off. So what I did, I factorized that, and this x plus 3. This x plus 3 and that x plus 3 are gone. That was my mistake. Okay, so then I will have x minus 3, x to the minus 3, are either from right or from left. But when I put minus 3 here, it becomes minus 1 over 6. So that was my mistake. So that was good that we checked with GeoGebra. So I did the example right. Yes. That was my point. I just wanted to show you that whenever you find the candidates, might be one of them is not real. And then it is guaranteed. So x equals to minus 3 is not a vertical asymptote. Only x equals to 3 is a vertical asymptote, and the graph on GeoGebra actually confirms that. Do you agree? So you see, if I show you this picture, x equals to 3. Let me just also draw x equals to 3. Yes, and now let me change the color so that you can see it better. Okay, so this red line that you see here is the vertical asymptote for this function. Yes? But you see there is no minus 3 as a vertical asymptote, even though minus 3 popped out here. It is a candidate, but when we checked it more, it is a fake one, so it is not correct. So it is extremely important. So it is a little bit convoluted when it comes to vertical asymptotes. And then finally, let me just talk about tangent. What is tangent? So f of x equals to tangent. So two examples I want to mention. Tangent that Gustav mentioned, and the other one, ln function. Okay? Okay, so tangent doesn't have is not a fraction, but it is a fraction in disguised form, yes? Because tangent is sine over cosine. So if I want to find the candidates of the vertical asymptotes for this function, I write it sine x over cosine x, and then I told you, you put cosine x equals to 0. These are candidates, but then you can immediately confirm that all candidates are real here. Why is that? Let me calculate. Where cosine becomes 0? Cosine becomes 0 if x is n pi plus pi over 2. By trigonometric equations we learned before, yes? That's the answer. And then n belongs to z. So how many vertical asymptotes I have for candidates? All of them are candidates. Are they really vertical asymptotes or not? Why? Because at these points that cosine is 0, it means that I am either on this top point or in this bottom. At each one of them, sine is either 1 or minus 1. So, and then if I divide 1 or minus 1 by 0, it becomes positive or minus infinity. So they are all real. Yes? So you get infinitely many vertical asymptotes. But what about ln of x? Do you think ln of x is one of those cases which is not fraction at all? But do you think there is a chance for ln of x blows up or goes to minus infinity at some number? And the answer is yes, okay? So the answer is that the limit of ln of x, when x goes to 0 from the right-hand side, it becomes negative infinity. So this is the case. So this means that x equals to 0 is the vertical asymptote. Yes? So I can just draw. By the way, it is not hard to convince yourself, hopefully. So you know that ln of small numbers becomes negative, yes? ln of 1 is 0. But ln of 1/2, do you agree it is negative or not? Because ln of 1/2 is minus ln of 2. So it is negative. And then ln of 1/3 is negative of ln of 3, even more negative. So by increasing this number, I am making my ln more and more negative. So when I make this number smaller and smaller, I am making ln negative and negative and negative. Okay, so let us check these two and then have a nice weekend, yes? You are lucky because we have to be here in the school tomorrow because of this Asymptotes.
Oh, really?
Yes. That's really unfortunate.
Can you hide in the aula?
I hope that the Daniel hears it. I don't want to cover it up. Okay. So what did you say? You said something?
Not really.
Okay. So let us check. What Gustav mentioned for tangent. So this tangent is the extreme example. Remember that. So y is equal. By the way, you should remember the graph of tangent. Yes, we had it in long back.
Yes.
So all of them are vertical asymptotes. Yes. Yeah. So yeah, we have infinitely many vertical asymptotes. For example, one of them is which one? Let's draw that. Pi over 2. So one of them is x equals to pi divided by 2. And this is one. This is one of them. And then, of course, later you will have another one. So you have infinitely many, you have infinitely many, this one. But let me also draw the last one, and then we will finish. So ln of x, y is equal to ln of, ln is not defined in GeoGebra? Or is it? It's defined. And you see the behavior here. Okay, but still you think, you get this impression that they are exactly on top of each other, which is not, yes? So if I want to make it more clear, so I can just make it more clear. So you see the deviation is actually quite a lot, okay? But it's breaking down. So it goes beyond the calculation or power of GeoGebra probably, but this is wrong, you know, it should be smooth.
Really?
Yes. Okay, any questions?
No.
Okay, thank you very much.
Thank you.
Just wait, don't show your heads.